You know, we count on the sun every single day, but what's wild is that it has a surprisingly unsteady heartbeat. For centuries, we've known its activity rises and falls, but every now and then it almost stops. So today, we're going to dive into a new model that's finally helping us understand why our star is just so fundamentally unpredictable.
We tend to think of the sun as this constant, totally reliable furnace in the sky. But history tells a really different story. Sometimes, for decades at a time, its activity just flatlines. So the central mystery we're tackling is what on earth causes our star to go quiet?
And check this out. This timeline shows the problem perfectly. You can see the sun's regular 11-year pulse just ticking along in the late 1700s. But then, bam, we hit what's called the Dalton minimum, a nearly 30-year period where activity just collapses. These long, mysterious lulls are known as grand minima, and for solar physicists, they are a massive puzzle. So that brings us right to the heart of the matter, the sun's regular heartbeat. We really need to unpack why this 11-year cycle, which is like a vital sign of the sun's magnetic health, isn't nearly as reliable as you might think. Okay, so to understand this irregularity, we have to find what's driving the whole cycle in the first place. And the prime suspect? It's a powerful magnetic engine, or dynamo, churning away deep inside the sun. Now, it's not mechanical, but it's this incredibly complex process that generates the sun's enormous magnetic fields. The leading theory for this engine is called the Babcock-Leighton mechanism, and basically what this theory says is that the sunspots we see on the surface, they aren't just a side effect of the solar cycle, they are a critical part of the engine itself. They actually help generate the sun's main north-south magnetic field. Okay, so let's break this engine down. Step 1. Deep inside, the sun's rotation stretches magnetic fields into these powerful east-west bands. Step 2. Loops of this magnetic field rise up and burst through the surface, creating what are called bipolar magnetic regions, or, pairs of sunspots. Step 3. On the surface, massive flows of plasma carry the magnetic energy from these dying sunspots up towards the poles. And finally, step 4. This energy gets dragged back down inside, becoming the seed for the next cycle, only now its magnetic direction is flipped, kind of like reversing the poles on a bar magnet. This whole feedback loop is the sun's magnetic engine. So, understanding this process is one thing, but trying to simulate it on a computer, whoa, that is incredibly difficult. So a team of researchers took a really clever approach. Instead of building one massive, super complex simulation, they built a virtual sun by connecting two separate, highly specialized models. They call it the 2 by 2D hybrid model, and the name comes from exactly what it does. It couples a two-dimensional model of the sun's surface with another two-dimensional model of its deep interior. By linking them, they can create a much more complete picture of the full magnetic cycle. Probably the best way to think about this is like having two different specialists working together. One is the surface expert. It uses a model called surface flux transport, or SFT, and it's a pro at tracking how magnetic fields from sunspots spread across the surface. The other is the interior expert, using the flux transport dynamo, or FTD model. And its job is to simulate how those deep, powerful magnetic fields are generated and moved around inside the sun. So here's how these two specialists talk to each other to create the full picture. The interior model makes the deep magnetic field that erupts into sunspots. Then the surface model jumps in and tracks how those sunspots decay and spread out. All that activity on the surface creates the new magnetic field at the poles, which is then fed back to the interior model to seed the very next cycle. It's this perfect, self-sustaining feedback loop. But look, having a cool model is one thing. How do you actually know if your virtual sun is, realistic? Well, you have to teach it. And this next step, calibration, is absolutely critical. It's where the simulation gets put to the test against cold, hard data from the real sun. So how in the world do you do that? I mean, the model has 18 different adjustable knobs and dials, things like the speed of internal flows or how fast magnetic fields diffuse. You can't just guess your way to the right answer. You need a systematic way to find the one combination that best matches reality. To solve this puzzle, they use this incredibly smart tool called a genetic algorithm. It's actually inspired by natural selection. It starts with a whole population of models, each with a random set of parameters. It tests them against real solar data, keeps the fittest ones, and then breeds them to create a new, better generation. After hundreds of rounds of this digital evolution, the best possible solution emerges. And the result? Wow. It is an absolutely remarkable match. On the left here is a butterfly diagram from the real sun. It plots where sunspots show up over time, and it gets its name because they start at the mid-latitudes and then drift towards the equator, creating a shape like a butterfly's wing. And on the right, that's what the optimized model came up with. The resemblance is just striking. We're talking a 94% correlation. The model had successfully learned the sun's magnetic fingerprint. Okay, so the model is calibrated, it knows the rules, but this is where we get to the big reveal. What happens when you just let this virtual sun run for hundreds of years all on its own, governed only by these rules? What's the secret ingredient to its long-term behavior? Well, the secret ingredient, it turns out, is randomness. The researchers didn't program the sunspots to be perfect and uniform. Instead, they built in the natural scatter we see in reality. Real sunspots have random variations. Some are a bit bigger, some are tilted a little differently, some pop up in slightly different places. This is known as stochasticity, and including it was the absolute key. And hey, don't just take my word for it. The researchers themselves put it perfectly. They state that this randomness isn't just noise in the system. It is the primary source of the sun's unpredictability. It's not a flaw in the model, it's a fundamental feature of the sun itself. And here is the power of that randomness in action. Get this, when the researchers just let the model run on its own, it spontaneously produced a grand minimum, a long quiet period that lasted for 4 full cycles, looking just like the historical Dalton minimum. They didn't program it to do this, it just happened, all because of the random chance in how the sunspots emerged. But wait, it gets even more dramatic. The researchers ran 30 long-term simulations, each starting with a different random seed. In nearly a quarter of them, 23%, the dynamo didn't just get quiet, it shut off completely. All it took was an unlucky streak of weak or poorly tilted sunspots to bring the entire magnetic engine of the sun to a grinding halt. And this all leads us to the single most important takeaway from this whole thing. The sun's unpredictability isn't some flaw in our understanding of our models. It's a fundamental feature of the star itself, driven by the built-in randomness of every single sunspot that forms. And that leaves us with one final, fascinating, and kind of mind-blowing question. We now have a model that shows the sun's magnetic engine can just spontaneously shut down. So if the dynamo that has powered our star for billions of years is ultimately governed by the roll of a dice, what does that mean for its future? Could it one day just turn off and stay off?